numerical on the radiation shield. Now this is the numerical. Okay, a double wall flask may be idealized to be equivalent to two infinite parallel plates. The emissivities of the wall are zero point 0.3 and zero point 0.7. The space between them is evacuated, means there is a no convection or conduction. A shield of polished aluminum of emissivity 0.05 is inserted between them. Find the reduction in the heat transfer due to the insertion of the radiation shield. Okay, what is given? It is say that there is a two double wall flasks may be idealized to be equivalent to two infinite parallel plates. So there is a two infinite parallel plates and their emissivity of the walls are given 0.3 and 0.7. The space between these two walls is evacuated, and in between these two walls a shield of polished aluminum of emissivity 0.05 is inserted between them. Find the reduction in the heat transfer due to the insertion of the radiation shield. Okay, now let's see the solution of it. So this is the one wall. Okay, and this is the another wall. The one wall having the emissivity wall 1, and this is the wall consider the 3. Okay, why we consider the 3? Because we are introduced the third one, that's why we take it is 3. Let's consider E1 is the emissivity of the first wall. The temperature is T1 of the first wall, and the emissivity of this third wall is 0.7, and the temperature is T3. Okay, so this is the condition. So though they are not mentioned the temperature or the area, but we are only interested to find the reduction in the heat transfer. We can find in terms of the percentage. Okay, now this is the first plane, this is the third plane. Emissivity is given 0.3, emissivity is 0.7. The temperature we consider the T1 is the temperature of the first wall, T3 is the temperature of third wall. Why I am taking this one? Because in our derivation we take this is third plane. Okay, and it's very easy for us to remember the parts of it. So this is the case what? When there is a no shield condition. Is there any third surface? The shield surface is present? No. For that one, we are writing the equation. So the radiant heat transfer rate is Q is equal to sigma into A as it is T1 raised to the power 4, T3 raised to the power 4, because the exchange of heat between this wall 1 and wall 3 upon the emissivity of the first wall upon the emissivity of the second wall. Now put up the values of it, whatever be the given, and consider the remaining value as it is x. Okay, next case. So this is the first case. Okay, I'm just giving you, and then after that one you just solve it whether you get the same reading or not. Now the second condition given, let's consider this is the wall 1 and this is the wall 2. Wall 1, wall 3. Okay, and emissivity is 0.3 as it is, and T1 here is the E3 is 0.7 and T3. Now this is the condition, but they say that there is an aluminum shield is introduced in between. So this is the aluminum shield is introduced, which having the good reflectivity, it having the shining one. And for that one, what is the emissivity? Emissivity is given is 0.05. Now E2 is the emissivity of the the second plane which is we introduced. Okay, so the third plane is introduced in between here, between the two walls. Okay, now for this case, what will be the equation? Now we are writing the equation. In presence of the shield, the radiant heat transfer rate is, this is the equation, just we solve in the derivation. What? The Q1 is equals to the sigma AT raised to the power 4 minus T2 raised to the power 4, the second surface, upon emissivity of the first surface minus emissivity plus emissivity of the second surface. And again the heat is transferred between this surface to this third one, second to third. And for that one, we have this equation between these two planes. Okay, between these two planes, we have this equation. The sigma into A T2 raised to the power 4 minus T3 raised to the power 4 upon 1 upon E2 plus 1 upon E3 minus 1. Okay. Now what do I do? First, I am equating these terms. Okay. And I write in terms of the T2. Just like a derivation, you follow the same steps. Okay. So what I do, I just introduce this putting the value of E1, E2, E2 and E3. Okay. And then I am equating in terms of the T2. And what I do there again, then I put it the value of T2 somewhere here, and again I find what is the value of Q1. So once I put it this T2 here, okay, again I solve this equation, I get in terms of this one, and this is the Q1 is equals to the X upon 42.76. Now this what X is what? The unknown values which is not mentioned, just like a temperature, and the area is not given. So we are not taking that values. We say it is a X. And now we are interested to know what is the percentage reduction of heat transfer. Now the percentage reduction in this case, it is the Q without shield minus Q1 is with shield upon Q without shield. Now once you put it the values of this Q1 here and the Q value is here, and upon Q you will get the reduction in heat transfer is about 91.2%.